Have you ever wondered how electric currents manage to create magnetic fields around them, even in empty space? Imagine a straight wire carrying electric current. Now picture invisible magnetic lines wrapping around it like loops. This very observation led to one of the most elegant laws in electromagnetism, Ampere's Circuital law. Ampere's law tells us that if you walk along a closed path around a wire and adapt the magnetic field at every step, the total you get is directly proportional to the current enclosed by that path. Mathematically, it's written as integral of B dot dl equals mu naught times I enclosed. It's a beautiful symmetry, and it becomes powerful when the current distribution itself is symmetrical. As you'll soon see, this law is the go-to tool for calculating magnetic fields around straight wires, inside solenoids, and even toroids. Let's now zoom in on the math behind Ampere's law. The integral, written as the closed-loop integral of B dot dl, tells us that we are summing up the magnetic field component along a path all the way around a loop. And here's something important, that loop must be closed, no loose ends allowed. Now here's the catch. For this formula to be practical, the magnetic field, B, should remain constant in both magnitude and direction along that chosen path. And when does that happen? Only in cases of neat symmetry, like a perfectly straight wire or a solenoid. When symmetry is present, this integral simplifies beautifully. We also have the magnetic constant mu naught. Its value is equal to 4 pi times 10 to the power of minus 7 Tesla meter per ampere. This tiny but fundamental constant links current with magnetic field. So let's apply it. Imagine placing a circular loop around a straight wire carrying current I. The magnetic field at a distance r from the wire comes out to be B equals mu naught times I divided by 2 pi are simple, elegant, and incredibly useful. This is the power of Ampere's law. Now, when do we pull out Ampere's law from our physics toolbox? Anytime we are dealing with symmetrical current distributions. For example, an infinitely long straight wire, a long solenoid, or a perfectly circular toroid. In these cases, magnetic field lines are neat and predictable, making the integral easy to evaluate. But, and this is important, if the setup is asymmetric, Ampere's law becomes tricky to apply directly. That's when we shift to the Biot Savart Law or more complex integrations. You can think of Ampere's law as the magnetic cousin of Gauss's law in electrostatics. Both thrive on symmetry and simplify our work when nature is tidy. Let's apply Ampere's law to a very classic situation, a long straight wire carrying a steady current I. Imagine drawing an invisible circle around the wire. That circle is our Amperian loop with radius r. Because of symmetry, the magnetic field at every point along this loop is tangential to the circle, and its magnitude is the same everywhere. Now, when we apply Ampere's law, the integral of B dot dl simplifies to be multiplied by the circumference of the circle, which is 2 pi r. On the right-hand side of the law, we have mu naught times I, where mu naught, the permeability of free space, equals 4 pi times 10 to the power of minus 7 Tesla meter per ampere. So, solving the equation, we get B equals mu naught times I divided by 2 pi r. This elegant result tells us something very important. The magnetic field decreases inversely with distance from the wire. And visually, as you can see in the diagram, the field lines wrap around the wire in the form of concentric circles, perfectly matching what the math predicts. Now let's switch our focus to a solenoid. Imagine a tightly wound coil of wire, almost like a spring. Inside a long solenoid, something remarkable happens. The magnetic field inside is uniform, straight, and perfectly parallel. These are the ideal conditions where Ampere's law shines. Picture a rectangular Amperian loop with one side running through the interior of the solenoid and the rest outside. Outside, the magnetic field is practically negligible, so all our attention goes to the inside segment. Now we apply Ampere's law. The equation becomes magnetic field B multiplied by length L equals mu naught times N times I times L, where N represents the number of turns per unit length and I is the current in each turn. Notice how the length L cancels out. What remains is beautifully simple, B equals mu naught times N times I. That's the magnetic field inside a long solenoid, uniform, predictable, and elegant in its simplicity. And this principle is more than just theory. It powers real-world marvels, electromagnets, MRI machines that peer inside our bodies, and even futuristic maglev trains that glide without touching the tracks. Alright, let's try a quick calculation using Ampere's law. The question is, what's the magnetic field at a distance of 5 centimeters from a long straight wire carrying 10 amperes of current? Step 1. Recall the formula. B equals mu naught times I divided by 2 pi r. Now let's plug in the values. Mu naught is 4 pi times 10 to the power of minus 7. The current, I, is 10 amperes. And the distance, r, is 0.05 meters. So the equation becomes B equals open bracket 4 pi times 10 to the power of minus 7 multiplied by 10 close bracket divided by open bracket 2 pi times 0.05 close bracket. When we simplify, notice that pi cancels out. What remains is B equals 4 times 10 to the power of minus 5 Tesla. That's equal to 40 microtesla, which, interestingly, is almost the same as Earth's magnetic field strength. Pretty amazing, isn't it? Let's quickly revisit the key ideas from Ampere's Circuital law. It gives us a direct link between current and the magnetic field it produces around a closed loop. But the magic lies in symmetry. We used it to derive magnetic field for a long wire where B falls with distance and for solenoids where B stays constant and strong inside. The law shines brightest when magnetic field lines follow a neat, predictable path. So to sum up, whenever you're faced with a symmetrical current distribution, think Ampere. It'll save you time and show the beauty of physics in action. I hope you now have a solid grasp of how current and magnetism are linked through this powerful law. See you in the next session where we explore even more exciting magnetic phenomena in the world around us.